Okay, well, let's get started. So today, we actually have some work to do. Tuesday was giving you an outline of one of the methods of calculating the epsilon machine, given the description of a process in terms of the word distribution. So hopefully that's clear. And then there are two problems on the current homework, which are to complete the probabilistic reconstruction for the golden mean and for the even process. I did, if you noticed on the home page, make a little note, I went back and fixed the topological reconstruction for the golden mean process. Those slides were wrong. I just, at the last minute, copied the wrong machine over, so it made no sense. But it's now corrected, so you can go back and look at that. The online lecture will have the wrong slides, but the PDF and then the HTML for the slides are now corrected. So you can step through that. I mean, you probably would want to read that as you got ready to do those problems. Okay, but today I want to address the question of why you should care. Why should one care about this set of causal states and transition dynamic? In motivating the construction, in talking about how we start out with prediction, and then that leads us, interesting enough, to this kind of structural view of process. I kept hinting at why this is important, but we mostly focused first on the formalism and then on the algorithmic side of it, which kind of brackets the idea. So hopefully there's some sense of the kind of underpinnings of how it works concretely. But the real question is, okay, imagine you're successful and you actually have one of these things in your hand. What does it tell you about the process? So that's what today is, and there's really some work to do. Namely, it's a number of results, basically theorems and propositions, corollaries, whatnot, and kind of proof sketches of how they work. The longer, more detailed proofs are in the Computation Mechanics article. Today I will give what I'm going to call proof sketches. Sort of think back to Cover and Thomas when you were reading through, and he introduced various properties of information gain. The kind of proofs that the Cover and Thomas book gives are kind of this higher level, not detailed, very technical, but at least they're kind of constructive and give you an intuition. So that's my goal today, to establish the main properties of the epsilon machine. So here we are, back at the Learning Channel. Finally, after many weeks, we're really addressing what a modeler should do, or an intelligent agent, or a piece of neural tissue, in principle, that helps an organism survive. What should it be doing? So the claim here is, and we're sort of answering this in principle, practical issues will come later. There were two basic questions, which really came from how we introduced dynamical systems. Right? So we're looking for a dynamical system. What are the states, given this impoverished view, this inaccurate instruments reporting of what's going on in the hidden box? And then what are the equations of motion? What are the dynamic over these states? And the claim from the past two lectures is that these are now answered. What are these effective states? What are the causal states? What are they effective for? They are effective for prediction. What are the equations of motion? Well, it's really the causal state transition structure, and the net result is this epsilon machine, set of states and transition matrices, symbol labeled transition matrices, and those form a kind of hidden Markov model that has a number of properties that we'll establish today. And then once we get the properties established, you say, oh, given we have these properties, A, what does that tell me about how a process is organized and how random it is? And also, what other things can I calculate if I have this epsilon machine? And the answers will be relatively sweeping. Okay, so just to recall, epsilon machine is this set of causal states and set of transition matrices, measurement symbol labeled transition matrices. The sort of first real lecture was trying to motivate this equivalence relation, predictive equivalence relation that induces the causal states, right? So we just group histories together when conditioned on those particular histories, the view of the future is the same. In other words, don't make distinctions between particular pasts if they lead you to the same future, view of the future. you can either think of this as incredibly obvious or profound. Certainly in terms of the consequences, it's a surprisingly powerful idea, and I'll try to convince you of that today. So we have this set of causal states. Maybe algebraically we think of we have this space of histories, and we mod out by this equivalence relation. We end up with this set of causal states. There's always a unique start state, and then once we have the causal states, we can use the causal state filtering. At every moment in time, we do have a history. We can use the epsilon function to look up for the particular history we've seen what causal state we're in, and then we can see what the state-to-state transition structure is. So we can pull out from actually the original data, we can pull out these transition matrices over the causal states. So causal states have several things attached to them. They are a set of histories, an equivalence class of histories. They have names, 0, 1, 2, 3, Alice, Bob, Charlie, doesn't matter. And the future morph. Each causal state is making some statement about what the future is going to look like. Principle determine the future past condition, future distribution, and then these transition matrices. So there's this overall process, which we did, I should say procedure, which we did on Tuesday. We can start with some description of a process. This can be obtained any number of ways, by observation, by starting with, say, a physical or biological model, figuring out what behaviors occur in their distribution. We then calculate these future morphs, search for them on the parse tree, and then we end up with the causal states in the transition structure. Okay. There's always this unique start state, which corresponds to lambda means the null symbol. I haven't made a measurement yet, so I don't know what causal state the process is in, and then I start making measurements, just like for the period 2 process. Initially, it's a fair coin because zeros and ones are for equal probability, and then I have to make a measurement, and then I know I'm in the odd or even phase of the period 2 oscillation. There's a probabilistic way of thinking about it where I can describe the modeler's view of what's going on, or my ignorance. I don't know what state the process is in. That corresponds to putting all the probability, state probability on this start state. And then we can sort of watch step by step how this flows down into the recurrent states and settles out. And then in the generic case, we're going to have transient states that we visit for some period of time, and then we make some transition down to a set of recurrent states. Typically, there's just one recurrent component. And then we rattle around in the recurrent states asymptotically in time. Now, this picture is helpful because it looks like what we were talking about before in the winter quarter in terms of Markov chains and hidden Markov chains. This presented to you here, it is a hidden Markov chain, okay? Edge-labeled hidden Markov chain. Actually, the mathematics we've introduced is much more powerful than this, and it depends on the nature of the process. In particular, things don't have to be finite state. It's okay to think about this finite state Markov chain or hidden Markov chain. That's fine to get started. But in fact, there are a number of cases we're going to analyze where you actually have a countable infinity of causal states. So this is just one example. And in fact, this is the Epsilon machine for something we've already studied and done calculations for. Like you started to do this in the first homework 10, the simple non-unifilar source. It turns out the simple non-unifilar source has an countable infinity of causal states. You start to get some sense of that, well, mostly because the reconstruction algorithm kind of tops out pretty quickly if you're doing it by hand. So there are other ways to get to this thing. But even more interestingly, or maybe more of a challenge, is that there can even be some sort of fractal set of causal states, some partial continuum of causal states. Now, this isn't obvious, but I just want to let you know that the definitions in the framework we've already set up for some class of process actually can induce this. In fact, the examples I'm showing you here, whether it's that simple non-unifilar source or this one, or even this one, a continuum of causal states. These are processes generated from sort of randomly selected hidden Markov chains that are non-unifilar. So, and in some sense, converting to the epsilon machine, is, as I'll prove to you today, is changing that model to a unifilar model. And the consequence is actually generating this distribution. So you might say, yeah, just make this a little bit plausible. So this is actually a three-state hidden Markov model. It's non-unifilar. I have states A, B, C. And the causal states, if you think of yourself as the observer, describe your best prediction of the distribution over these states, given the observed symbol 0, 1, 1, 0. That'll lead you to a particular distribution over states. When we have just a finite set of causal states, then typically, if you see a sufficiently long word, you'll always end up with a delta function distribution of one particular state. That was the problem of synchronization we talked about. Turns out, for these non-unifilar Markov chain processes, this problem of synchronization is much more problematic. You never end up with just knowing its probability. All the probability is in state B, or the process is in state C. So this is actually a simplex. It's a distribution over three states. Every point in here is a combination of numbers that add to one, positive, and 0 and 1. So the kind of simple finite state case I first showed would be, you kind of eventually, after you've seen this or that word, you know what state you're in. You're just kind of hopping around. But in the general case, we have to think about very complicated sets of causal states. So, interesting, even for a finite memory process. So these are called the mixed states. So we'll come back to that in a couple weeks. But just so we don't think that all we're working with are, as my colleagues in computer science would think, oh, you're just working with probabilistic finite state machines. No, we're not doing that. These are rather rich dynamical systems. Excuse me. Okay, so now to start thinking about what this epsilon machine representation of a process is. Actually, sometimes I'll use the word presentation, partly because there can be many models of a given process. So sometimes we, in the literature, use the word presentation rather than representation. Okay, so in what sense is an epsilon machine a model of a process? Well, we can think of it as maybe we started with a process, we calculate the causal states and transition structure. We now have this particular kind of hidden Markov model. So one question would be, what does it describe about the process? Well, one way to think about using it is as if it were a generator. I now have a model, like in a sense, put it into a simulator and see what sequences it produces and what their probabilities are. Well, since we started with the process and claiming it's a good model process, it's intuitive that the epsilon machine generates the word distribution. It should. It's supposed to model that. So in what sense is an epsilon machine model of the process's word distribution? Well, so the word distribution is just the distribution of length 1 word, length 2 words, all length words, and it's supposed to somehow reproduce that. So let's look at a particular word of length L. So we have a series of measurements here, length L. And then the rule of using an epsilon machine is we always start in the start state. So I'm going to put unit probability in the start state. And then look at the transition structure. So the way to think about this, I have my epsilon machine, I put the probability distribution all in the start state. I don't know what's going on. That unique start state is a state of ignorance about what the process is doing. And then you make a series of measurements, and a particular word takes you through a particular path in the machine. And as you do that, you just, starting with this initial distribution, well, this is trivial. This is just the delta function on the start state. I just follow the transitions going from the start state to the next state, given that I saw the first symbol, times the transition probability that I went from the next state to the successor state, saying the next symbol, and so on. So I just follow a path through, and the whole time I'm just multiplying through a series of transition probabilities. Get down to the last symbol. That product is the probability of the word that's assigned by that epsilon machine. So in short, there's just a rather direct way of calculating. If we have the full epsilon machine with its unique start state, it's just really this telescoping product along the path that that sequence takes. Now, the way I'm describing this assumes something I'm going to prove very shortly, namely that the way I described it, it assumes unifilarity. Remember, unifilarity is if I'm in a state and I take a transition that's labeled by the symbol I just saw, I go to a unique transition and unique next state. Right? That was the problem with non-unifilar models, that this might be branching. I might go from A to B and C on a 0, and then this calculation would sort of branch out. I have to be following this increasingly large number of alternative paths that would be consistent with the observed word. Right? So we talked through that with a simple non-unifilar source and so on. Here, when I write this out, I'm actually assuming this unifilarity property. So I'll prove that to you. So this new presentation of a process, it's unifilar. In that case, there's just one path for the machine for every word. Up to some technical provisos, right? For example, if I say 0, there can be a number of transitions on a 0. That's why, in this first way I'm describing how the Epsilon machine produces the word distribution, we're starting from this unique start state. In that case, there's a single path through the machine.
If you start off synchronized.
Yeah, in a sense, you start off synchronized. By definition, there is this unique start state, which we'll have to establish. But, and then, since every individual transition is unifilar, there's just one alternative, and therefore I'm going to follow one path. Okay. So in a sense, unifilarity has this practical computational complexity advantage that calculating the word distribution, it's linear in the length of the words. Non-unifilar had this exponentially increased potentially set of alternatives I'd have to track, and that would be computationally more intensive. So now there's another way to think about this, which kind of contrasts with using the unique start state. You can also forget the transient states and assume I've just got the recurrent component, and then calculate the asymptotic state visitation probability. So this alternative approach to calculating the word distribution from a machine is to assume I start in any of the recurrent causal states with the given asymptotic state probability, and then I'm seeing the given word I'm interested in from that state. Now, of course, there might be some forbidden transitions, so a given word doesn't necessarily follow from every state, so you just keep track of that. Okay, so the way we do this is, again, go back to the transition matrix that describes the causal state Markov chain itself, calculate this left eigenvector normalized improbability, so that gives me the asymptotic probability visiting the various causal states. And then what we can do, and I'm using sort of Bra-Ket notation from physics here, but this is just this matrix product. We have this eigenvalue, think of that as a row vector, times this simple transition matrix, and then I just normalize. I add things up. So I can go from, I start in any state with this given probability that sort of flows one step through the machine, and then I add up the resulting probabilities to get the probability of a given symbol. That's just for one step. This extends to 2 steps. Same idea. Row vector times now this product of the symbol labeled transition matrix for the first symbol times the second symbol, and then I add them up with that one's column vector. So in general, this is how we calculate the word probabilities if we want to use this method of, I don't know what state I'm in, I'm going to assume it's the asymptotic state probability, and then I just calculate if I had 10 states or 10 paths I might have to follow. Typically, things get pruned off very quickly in terms of what are allowed start states for a given sequence. So, yeah. So any word here, you just think of this as just one matrix. We just do this matrix multiplication out, following the symbols, and choosing which transition matrix to use. Okay, so there are 2 ways to calculate the word distribution. Yeah.
Is there a reason to want to think about it this way? I guess what I'm thinking about is whether any of the other ways of generating an Epsilon machine would give you just 3 recurrent states, or
just 3?
Like, I mean, the method we wind up generating the Epsilon machine always gives you those start states, so we wouldn't need this method. But are there other ones that don't give you those?
Oh yeah. Right. Yes. Okay. Good. Right. So why have 2 techniques? Why not just use this first thing? Okay. So there are a number of things which we'll run across, but just to give you some idea of how complicated these things can be, which is a little bit hinting back to those examples I just gave of fractal continuum of causal states. So there's some methods, first of all, that assume basically just estimate the recurrent causal state. So, for example, I did mention this one thing, the causal state splitting reconstruction. Its sort of main ansatz is to assume you have an IID process, a single state, single causal state, and then as you collect data, you reach kind of a statistical threshold where it's, I see, no consecutive zeros if it was a golden mean process, then that gives you a statistical justification for adding a state that corresponds to remembering that restriction. If I see a 0, I must see a 1. So that sort of starts off, and that really focuses on just the recurrent states. The subtree reconstruction that we went through on Tuesday, actually, since we're starting at the top tree node, that's where the transient states are going to be if they're anywhere. That tends to include all of that in there. Now, practically, sometimes, even a sort of a process with a finite number of causal states can have an infinite number of transient states. So in that case, maybe I don't want to calculate. It's just easier for me to calculate the asymptotic state distribution on a 7x7 matrix. I have 7 causal states, and just do this. Okay. And so we'll talk about when that happens. So there are reasons. Okay, but really the main goal is to establish a number of properties. At the end of which you're supposed to go, I see why we should do this, as opposed to all my hand-wavy motivations before. So we're going to talk about causal shielding, how the causal states actually render the observed past and future conditionally independent. Like I already hinted at, we have to show that the epsilon machine is actually a unifilar hidden model. That the causal states have a kind of Markovian property of summarizing the past, maybe more operationally, that they're optimal predictors. In fact, there can be other optimal predictors, but the epsilon machine is one of those things, but they're the optimal predictor of minimal size. And in fact, if you come up with, you have your own favorite model, you say, here, it's optimal in its prediction, it's minimal size, then basically you and I are just disagreeing over what we call the states. Alice, Bob, and Charlie are 0, 1, and 2. And essentially, this presentation is unique. And hence, this set of properties strongly suggests this is what you should be doing in any modeling. Now, again, we've kind of hinted at and discussed very vaguely, finite data. There are all sorts of issues. What we're trying to establish here is kind of in principle, if we have a good model of the statistics of a process, what is the best presentation or representation for it? And we're extracting that from the data, getting the number of states and the transitions from the process itself, not imposing that like is typically done with a lot of hidden Markov model data analysis and modeling. Okay, so we just have this series of results to get through. Okay, so first thing, causal shielding. So what do I mean? I mean the past and future are independent if I give you the causal state. So the past is independent of the future if I know the causal state. In other words, you're trying to predict something about the future, and either you can remember the particular past that's taken you to this present time, or I can say, you're in state D. Somehow, those are equivalent kinds of information. Shouldn't be too surprising because causal states are made of the past. So, so how are we going to do this? So again, we'll just think of this process described by infinite chain of random variables with past and the future. And then what do I mean by, what's the probability definition of this conditional independence? So think of this as if I had probability of x and y given z, then I would say x and y given z. X and y are conditionally independent if this joint conditional distribution factors into the product of the two marginal conditional distributions. In this case, the distribution over the process, past and future, given the causal state, is the product of the distribution over past given the causal state times the probability of the future given the causal state. So the way we say this is that if you know what causal state you're in, it shields the past from the future, and the future from the past. It's symmetric. So very much like the states of a Markov chain do, but for hidden processes. Okay, so to prove this, we're going to use the properties that define the epsilon machine, and also kind of build up for the other properties I'm going to talk about, using shielding and unifilarity and so on. Okay, so what we want to do is we're going to take this joint conditional distribution and split it just by doing a probability identity here. Right? So we're just taking probability of x and y given c, and we just factor that out to probability of y given x and z times probability of x given z. That's just probability identity. These are equal. So in order to, basically what I have to argue to establish the property is that this dependence on the past disappears. In other words, that this factor here is really just dependent on the causal state. The idea is pretty simple. I'm in a causal state, but their histories lead to causal state. They're kind of, in a sense, they're redundant information. Well, that's the one. It's not too hard. So, okay, so what we're going to do is imagine we had some particular past. And we stick that into our epsilon function. It tells us what causal state we're in. Okay. So now, first thing I'm going to do here is just take this left-hand side and unpack it a little bit. So what the distribution we're really talking about is the distribution of the future, given what we saw, particular past, S prime, and then we're in some causal state. And maybe the causal state we're in, the exemplar in its equivalence class is some other past. Okay. But now, we wouldn't be in this causal state if these S prime and S not prime were different. They're essentially the same information. So in fact, this probability is the same thing as just looking at the future given this particular past. And what I'm doing is I'm basically just picking the particular past I've seen, this realization, picking S prime to be another exemplar in this equivalence class. They all lead to the same distribution. Okay, so that's sort of one way. However, this probability here, I can sort of go back. So I'm looking at the future conditioned on the particular past, but then I can also apply the epsilon function to that past to find out what causal state I'm in. Right? So this is just using the causal equivalence relation that these two distributions are the same. I can either condition on the past or the causal state that's in the equivalence class that leads to that causal state. So this ends up establishing that this probability here is just this sort of uncertainty in the future conditioned on a particular causal state. Doesn't depend on the history. I can just drop this. Or the other way I was saying is that knowing the causal state you're in and knowing what history has led to it, those are redundant kinds of information. So I can just factor that out. So we get this factoring. Okay, so that's slightly, as a proof sketch, it kind of hints at the sort of circumlocutions you have to go through to establish what is a relatively intuitive property, namely that pasts and causal states, as they're constructed, are functions of the past. Those are the same kinds of information, at least as far as predicting the future distribution goes. Okay, so that gives us the causal shielding idea. Good. Which tells us, gives us some interpretation of what these causal states are doing. Kind of operational property of causal states. Okay, so now, maybe a little more surprising. So the claim is that the epsilon machines are unifilar. So if you remember, right, unifilar means that if I'm in a given causal state at time t, and I see a symbol, there is at most one next successor state that I go to. So state A goes to state B or C, but it goes to A on a 0 and B on a 0 and C on a 1. I can't go from A to B and C, both observing a 0. Okay, so what does this mean? Now we have to say what this property is more formally. So we're assume we're in state I, and then we observe some symbol. What does it mean that we see at most one successor state, one successor causal state? Well, it means that here, if I'm in this causal state I, pick one of its histories, okay? But then if I see S, that gives me a new history at the next time step. And the claim is that that is in the successor state J, okay? So basically there are two different cases. If there is a next causal state, then we have to show that all the other successor states have 0 transition probability. Can't get there. Or it could be the case that I'm in state A, And on the 0, that's a disallowed transition. Well, and then in that case, we're just going to set the transition probability to 0. Okay, so that's the setup. So really, this boils down to assuming at time t, if we've seen these, well, not time t, if we've seen these two different histories, and we assume they're in the same equivalence class, then wherever we are, having seen S or S prime, at the next step, we see symbol S. So we assume we're going to see symbol S. And the claim is that this new history, S past S, is equivalent to S prime S. There. So right, at the previous time step, they're in the same equivalence class, and you go one step forward. Having seen the same symbol, you're in the same equivalence class. Okay, so the way to do this, a little bit, some notation here. So after we've seen some particular paths, we look to the future, and that's a set of sequences. So what I want to do, this whole set, what I'm going to do is just talk about the set of sequences that follow if, say, I saw a 0. So the idea here is that S is a particular realization, 0 or 1, say, and then F are all the sequences. It's called the follower set that you could see from that point. Okay, so the other way to say this is that this set of sequences, SF, these are all the future sequences I could see that are prepended by having observed S. Okay. So what's the consequence of assuming that we start here with two histories that are in the same equivalence class? Okay. Well, I'm just going to rewrite the causal equivalence relation. What that says is based on little s and s prime, I look to the future and their distributions are the same. So I've just written down that. Well, just focus on this up here. This is actually a joint distribution over next symbol, next symbol, next symbol, thought as independent random variables. I'm just going to break it into two pieces. This next symbol and then everything else, all the sequences. So I'm just rewriting the notation here so that I'm thinking of this not as this joint random variable, but now they've got two aggregate random variables. A single symbol random variable and then the sequences that follow after it. And same thing for here when we're conditioning on S prime. Okay, well, now we just apply probability identity, probability of X and Y given Z. We're just going to factor that out, probably Y given Z times the probability of X given Y and Z. Okay, so I can do that. Now the notation gets a little bit messy here, but it's just a probability identity. On the left-hand side you get this, on the right-hand side you get here, and I've just written this out, these products. So over here, I'm choosing to pull out S1 here. So this is the future starting one step after the next symbol, right? And then I'm conditioning on the next symbol being S and having seen that particular history, little s, times the probability of seeing the next symbol, individual symbol, and then it followed that particular history. Same thing over here, except all that's different is I'm conditioning on this different history S prime. Okay, but it's just an identity here, applying this for. But it turns out we assumed that, in fact, in going one step forward after both of these histories, S and S prime, we saw the symbol S. Okay, that means this factor and this factor here are 1 by assumption. We saw them. Also, I say stationarity here because it could be that when I saw S and S prime, they could have been separated by some time. So I have to assume the probabilities aren't changing. So that's stationarity. Probability. Conditional probability, word probabilities don't change based on the origin of time. Okay, so that's 1. If I drop those out, I end up with this. Right? So, and all we're doing here is, if I've gotten rid of this factor of 1, I'm just packing back together. I saw this particular history S, and after that, I saw the symbol S. So I now have a new history in the sense of the next time, which is that past plus the new symbol. And then we have this new, this is the follower set of the symbol sequences I saw after one measurement. And these are the same, whether I started with history S or S prime. These future distributions are the same. Well, that's this criteria here. Namely that this history and this history are in the same class because conditioned on those histories, I have the same distribution over futures. Yeah?
It doesn't really matter, but it seems like you didn't even have to assume that that's one because those two probabilities have to be equal because...
We assumed them in a sense.
What's that?
We assumed them.
I guess that's true, but even
that we're
even
seeing.
If you don't, the fact
Yeah.
that those probabilities are equal just follows from them being the same because that's the history, right?
Yeah.
Yeah.
Yeah. Yeah.
These have to be non-zero.
Right. So there's a
Yeah.
case here, right? Yeah, right. In some sense, I'm dividing. Yeah. So it's either right. There's a case here. What happens if it was disallowed? Well, I was kind of in the assumption, assuming that it did occur. But you're right. In the paper, you'll see you have to deal with all the dotting of the I's for that kind of thing. So this is it's maybe the shielding is kind of, I don't know. I find it a little bit intuitive given how the causal states are constructed. This unifilarity is a little bit surprising. It's a pretty powerful property. I mean, like the reason I was emphasizing it through the winter, it leads to very computationally useful things in terms of, an observed sequence corresponds to one path over the internal states and so on. We needed to calculate entropy rates, all sorts of consequences for this. So it's interesting how just assuming this predictive equivalence relation, we're getting a non-trivial property like that. So why do we care about unifilarity? Well, there's this more or less one-to-one mapping between the internal state sequences and the observed simple sequences. That's nice. We can calculate properties of internal state sequences, which are just Markov chains, to make statements about the observed sequences. In particular, the most immediate one is to calculate the entropy rate. If you remember the formulas we used, right, the state average branching uncertainty, that assumes unifilarity. It only works with unifilarity. So it's really dependent on having some model of your process. Even if you just want to figure out how random the thing is by calculating the entropy rate, you need this. So the sort of bold claim is, however you're calculating, and there's a long history since the beginning of information theory of given models of stochastic process, how do I calculate or can I calculate entropy rate? Basically, they're all equivalent to somehow finding these causal states that have this unifilar property. So you can't get away with this. You might call it something else, but it's somehow you have to find these causal states or somehow be using this predictive equivalence relation. Some methods it might seem rather implicit, but okay. What about the causal state process itself? So it turns out that it's a first-order Markov process. Right? Going from data, get causal states. Through causal filtering, I can take each observed history and turn it into this causal state, that causal state at different times. I now have the stochastic process over these causal states. Well, a priori, that could be a really complicated process. But it turns out it's first-order Markov. The causal states really are capturing a lot of the historical information in the present moment. So what do we mean by this first-order Markov? Remember, Markov process, the general process, the next variable can depend on arbitrarily long past. If it's first-order Markov, all that's relevant is the value of the variable at the previous time step. So again, and then you look at this, it really is, the causal states are summarizing the past this way. Okay, so the sketch of the proof, we'll just do it for assuming that the current variable just depends on the previous two steps. And then we want to show that it really just depends on only one previous step. Okay. And then you could, by induction, get up to longer histories. Okay, so what we're going to do here is look at this probability at time t, given where we are, state we're in at t-1 and t-2. I'm just going to add some notation here. We can assume this random variable, the next state I could be in, is in some subset of the causal states. Right? I can be in state D and go to E and F. So this is, again, just a statement about the internal chain. But now what I'm going to do is switch back to the labels on the transitions that took me to those two states. Why? Because that's where we just established some properties. So a lot of these proofs, we make this move going from the internal Markov chain up to the observed, some property you know on the observed sequences, and then back down again, or other way around. So that's kind of the trick in some of these things. So what we're doing is going from just talking about the internal state process to its proxy up at the level of the symbols that label the transitions that took us to the states in M. Okay? But we know, we just proved that up at the level of the sort of observed sequences conditioned on causal states, they shield, that we don't have to depend on this. So we're borrowing shielding, which we proved up at the observed sequence level, borrowing that here to show that we can get rid of the state 2 steps before, and then we just pop back down and change what we're concentrating on, the transitions and the symbols that label them, to the states. So causal shielding at the observed level leads to this order 1 Markov property over the causal states themselves. Okay, so things are simplifying here. Probably the most important property, or first important property, is that the Epsilon machines are optimal predictors. So, and now what do we mean by that? So I want you to think back to this sort of formal space of all possible candidate alternative models, rival models. The Epsilon machine's in there somewhere, but there are all these other choices I could make. So we're going to go back and start talking about how an arbitrary choice of model induces a partition over the space of histories. And the idea here is to establish optimality. What we mean is that the uncertainty in the future, given the causal states, is the lowest compared to any other alternative. If I condition on anything else, typically your uncertainty will be higher. Okay. This actually doesn't take too long, so let's just do some rewriting here. Let's focus on this guy. So conditioning on the causal states, we have this uncertainty over the future L steps ahead. Well, like we argued before, I can either think that I know what causal state I'm in, or I can just pick one of the exemplars in its equivalence class for histories. Okay. So this uncertainty given causal state is the same thing as conditioning on the infinite past associated with that causal state. That's fine. But we know that any rival model is going to be some function of the past. Remember, that was that Ada thing. We first introduced this notion of rival models. And it's sort of a version of the data processing inequality where basically if the event you're conditioning on, you take some function of that function, the best it can do, or typically what it will do, it will throw information away that was useful. So that, and you throw information away that you're used, in this case, to predict something, that can mean your predictions will be worse, that your uncertainty in the future is larger. So there you have it. Because the rivals are sort of arbitrary functions of the past, they can do no better than remembering the past, but the pasts are sort of well summarized by the causal states. So we end up with, in fact, they're equivalent to having the pasts. So all the other models must be worse predictors. A couple quick just observations, essentially. Remember, we had how random the process is based on different rival models. Well, you can show that if we choose the causal states, we actually end up with the process's entropy rate. Not surprising, because knowing the causal state is as good as knowing the past of the process. They just have good, concise summaries of it. So how do we do this? So the definition of the entropy rate of a given model class R is just, now I'm going to look at the block entropy conditioned on the model. Well, in this case, I'm assuming the causal states. Okay, so this is just a definition of the entropy rate in terms of the block entropy growth rate. I can move from knowing which causal state I am to just focusing on the histories that are associated with each causal state. Now, here I have this future L steps ahead, and I want to think about that as L independent random variables. So this is actually a joint distribution. Next symbol, symbol after that, going into the future conditioned on this past. Well, it turns out that I can factor, there's the, from last quarter, there is a conditional entropy chain rule. We can factor that out and then shift time so that we're, based on different histories, I'm only predicting one symbol ahead. So you end up with this joint distribution. You can factor it into single time step predictions. Right? So this is actually L separate terms here, where we have this joint distribution for L thing, right? End up with a sum of L single symbol uncertainties, and then we have different histories we're conditioned on based on if we're predicting from two states going forward or not, and we can shift those in time by stationarity to get L times the single symbol uncertainty conditioned on the past. And that's just the entropy rate. And immediately corollary of the previous thing, now that we have this sort of optimal case, so the Epsilon-Machine gives you the entropy rate of a process. Any alternative rival model perhaps does as well, but typically would do worse. It'll assign a higher entropy rate. Just combining the previous proposition and then this lemma, we get this. So not only is it true for the predicting L steps ahead, it's also the case that Epsilon machines are optimal for getting the entropy rate of a process. It's also a rather direct corollary. Remember, we had this notion of the prescience. If I choose a model, how descriptive or predictive is it? Measure that in terms of redundancy. So you can show that the Epsilon machines are maximally prescient. They capture the most of the future compared to any other rival. So the rival models, we had this measure of redundancy being the difference between log of the alphabet size and then the entropy rate that our rival model induced there. Well, in the case of using the causal states, we just showed that this is the entropy rate of the process, and that was our total predictability, right? The predictability gain summed up. So basically, and this is almost a narrative rewording, basically the Epsilon machine is more prescient about the future, more predictive about the future than any rival. And that just follows from what we just established. The entropy rates are larger, therefore the difference is smaller for any rival. So in terms of goals, that's pretty good. So after doing all this work, you calculate the causal states and transition structure, and you have these optimal predictors. One way to think about this, and this gets back to the very first lecture on information theory, and there was this mysterious quantity, what is information? And I kind of mentioned my favorite definition was given my mentor, Gregory Bateson, an early cybernetician. Right? He defined information as a difference that makes a difference. So here we can see the causal states as capturing that. The causal states contain every difference in the past that makes a difference in predicting the future. That's exactly how that predictive equivalence relation is constructed. Right? We don't make distinctions between tasks that are predictably equivalent. What are we trying to do? We're trying to predict the future. So it actually kind of nicely encapsulates this concrete version of his kind of informal definition of information. So another way to say this, and we'll come back and I'll introduce this notion of sufficient statistics, the causal states are sufficient statistics. In short, anything you want to calculate about a process can be calculated from the Epsilon machine. So, but I'll prove that to you. Okay, so at this point, we've been talking about this entire space of models. Somewhere in there was the Epsilon machine, the causal states, and it could be anywhere out here. We're just picking these things. So just in terms of prediction, we showed that the Epsilon machine is the best, but it turns out there can be other models. that are equally predictive. So we call those the Prescient rivals. So you should imagine in the space of all these ways of, all these models we could choose, all these possible partitions of the space of histories, there's now a subspace where all these basically get the entropy rate. They ascribe the same apparent randomness to the process. Right? So the definition of these are choices of model where the future is equally uncertain compared to using the causal states themselves. Now, where we're going with this is actually trying to compare develop another optimality criteria for the causal states. We want to show that they're the smallest set that's predictive in this sense. But we need to do a little work first. So we have to go back to the space of histories and compare how rival models and the causal states partition up the space of histories. There's a little bit of internal structure here. So the result we want to establish now is that these equally predictive rivals are, the way they partition up the space of histories, those subsets or classes are refinements of the causal state partition of pasts. Okay. So we have two cases. So let me describe it graphically. So here's the space of pasts. And then I put in here with the solid lines the partition induced by these 5 causal states. Okay. And then there's sort of 2 cases for the rivals. Either a rival state, the set of histories associated with the rival state are completely contained in one of the causal states. Or the set of histories lays across different equivalence, causal state equivalence cells in the space of histories, and mixing them together. Okay. So if, in this case here, if one of the partition elements is completely contained in or equal to one of the causal states, then by definition they make the same prediction. Okay, so there's no real difference here. By the way, the future conditional distribution is the same. That's fine. Or a more interesting case here is when the rival partition cell contains causal state cells. So a number of those. Okay, and this is, in terms of vocabulary, this is not a refinement. It's a mixture of the partition elements. So the future predictions we would make, the future morph conditioned on R2 in this case, is going to be some mixture of the future morphs associated with S5, S4, and S3. Okay, I'm not going to say exactly what, but it's some mixture of these things, throwing these things together. So we'll just sort of write that out formally, that given R2 here, the predictions we're going to make on the future, sort of on average, will be hopping around, will be some mixture of the future morphs associated with the contained causal states, with some coefficient here. Does the right normalization to make these probabilities. Some mixture. Okay. Problem is that if you mix distributions, you increase the entropy. In other words, you make worse predictions. Again, we were sort of ignoring distinctions. R2 is ignoring distinctions between pasts that lead to different predictions, therefore you can't do any better. Or you do worse, I should say. And the way you show this is simple information identity, that the entropy of a mixture of distributions is bounded below by the sum of the individual entropies of the individual distributions, piece of I. So you get worse predictions with the rival, which is a contradiction, because we started out assuming that we had prescient rivals that had made the same predictions over the future, same uncertainty about the future. So that's a contradiction. Therefore, this can't happen. This can't happen. This second case can't happen. This can, that's fine. They agree. So the conclusion is sort of shown graphically here, is that if whatever alternative model you want to give me, if you're predicting at the same error rate, assigning the same uncertainty to the future, then the induced partition over the space of histories has to be a refinement, right? Either wholly contained, or at least the boundaries of the cells have to respect the boundaries of the causal state cells, like that. So it's kind of obvious. There can be more of them, and certainly no fewer, because then it would start to mix the cells for the causal state partition. Okay, so now with that kind of graphical picture of what's going on here as we compare different models, we can now establish the second sort of optimality property of epsilon machines, namely that they're the smallest. Of all the prescient rivals, all the models that you would have that would give you the entropy rate or predict optimally, the epsilon machine is the smallest. Well, what do I mean by small? Well, what I'm going to do here is I could talk about numbers, like I was just doing with the refinement picture, but our measure of model size is the amount of state information. So we're going to use the statistical complexity of your rival model, your prescient rival, and compare that to the amount of state information in the causal states. And the claim is that the best you can do is equal this, and typically your choice of alternative predictive model will be a larger model in this sense. It means you have to use more state information to do predictions. Okay. So, proof sketch. Okay, so the prescient rivals are refinements. So the way to say that previous picture formally is that if I know which rival partition cell I'm in, because of this refinement property, I know which larger causal state cell I'm in. So there's some function, whatever it is, that will map me, because these are a more refined picture. They'll always be a map from the rival partition cell element to the causal state that contains it. Okay, so there's such a G. However, we have this basic information inequality here. If I have a random variable that is it's uncertain to some degree, some entropy, if I take a function of that random variable, well, all this function can do is either be the identity or throw information away, confuse things, throw away events. Therefore, to contract the distribution and make it less entropic. Okay, so the entropy rate of random variable is always greater or equal to than the entropy of the function, some function of the random variable. Well, that's exactly what we have here, right? We have C mu is just the Shannon information in the causal state distribution. Well, we just argued that actually these are a function of the rivals, and then applying this identity, it means that this state entropy has to be less than the state entropy of the rival. Right? It's more refined. There are more elements. A simple way to think about this would be, well, we're using p log p here for the Shannon information in these distributions. Imagine it was uniform. Then we're really just counting states, right? Whenever the event probabilities are equally likely, p log p turns into just log of the number of events. So that's why I say, it's the first cut. It's easy to think about the C mu as just being model size. But this is more general. We're talking also about the distribution of the states. So the epsilon machine size, the statistical complexity, or the state information it has, is less than or equal to any other equally predictive model. So within that subspace, so these are all the equally predictive prescient rivals. This one, the epsilon machine, is the smallest. Well, so one of the consequences of this is that, and we'll come back to talk more about this, but that the statistical complexity measures the amount of historical information that the process stores. And the key point I want to make here, we'll come back and talk about sort of operational interpretations of these different entropy measures, but I just want to make this kind of presage this a little bit. This kind of interpretation wouldn't be true if we were using models, representations that weren't minimal. Right? I can take, just like the case of that rival partition, I can just start making all of these subsets and make an arbitrarily large model that's equally predictive. Well, but then I can't take the number of states to be the measure of memory because, well, first of all, it's arbitrary in that case. So here we have this criteria. We derive that the causal states are smallest in number that still do optimal prediction. It's a unique property. So that allows us to interpret properties of the model as properties of the process. So we're moving one kind of dimension of subjectivity that I could just make arbitrarily large models, even of a fair coin. Right? I could make a 100-state model as long as the branching transitions were all 50-50, but there's no sense in which the fair coin has 100 states of memory. Right? By definition, the past is independent of the future. So this is sort of implementing that. Well, you could say that, okay, yeah, you showed me that within the Prescient rivals, the equally predictive alternative models, the Epsilon-Machine is the smallest, but there could be other predictive small machines too. Why not? So it turns out that, in fact, the Epsilon-Machines are unique. And this takes just a little more work to do. Okay, so the claim is that Prescient rival in the same size, statistical complexity. So it's equally predictive, but at the same size, same statistical complexity, is essentially the same thing as the Epsilon-Machine, up to you and I disagreeing over what we call the states. Right? Alice, Bob, and Charlie, 0, 1, 2, ABC. Right? So the idea is, if we have a Prescient rival, and we're assuming that it has the same state information, statistical complexity as the Epsilon-Machine, then necessarily the state sets are equivalent. So how are we going to do that? Well, okay, so the first thing follows directly from the assumption that we have rival states. We're already established or talked about that there will be some G. Since these are refinements, I always know whatever rival cell I'm in, I know what the enclosing causal state cell is. So there's some function G. But this is actually going the other way around. Is there some F such that if I tell you what causal state you're in, you know what rival cell you're in? And one way to do this is just to not so much do a construction of these basic histories, but just look at this measure of uncertainty. So we're going to claim that there is such a function if we can prove that this entropy, this uncertainty, if it's the uncertainty in which rival cell I'm in, rival state, given I know what causal state. Okay. So what we're going to do is look at the mutual information between the causal states. Now we're thinking of these as a random variable. We're kind of hopping around between them, and then the rival effective states. Just look at mutual information, and then we're going to expand this in two different ways and compare. Okay. So the first way is we pull out, if you remember the definition of mutual information, is the uncertainty in the first variable minus the uncertainty in the first variable given the second variable. Right? So the uncertainty in the causal states, well, that's C mu of the Epsilon-Machine, minus the uncertainty if we knew what the Prescient rival cells were. I can also expand this in this complementary way. I can pull out the marginal distribution from this joint of the uncertainty in the rival states minus the uncertainty in the rival states given the causal state. So those are just information identities. Well, we just argued that there is no uncertainty. If I know what the rival cell is, I know what causal state I'm in. There's a function. It's determined. So that term is 0. So we just have this on the left-hand side now. And then on the right-hand side, okay, so we just rewrite this, get rid of that term. So now we have that the statistical complexity of the Epsilon-Machine is these two terms. But then we assumed that the state informations were the same. Right? We assumed this. At the same size informationally. So this and this are the same, therefore this term must be 0. So the uncertainty in the rival states given the causal states is 0. So again, it's not as constructive. I'm not giving you what the F is, but at this information level, we've shown that this function from causal states to rival states must exist again. So right, the rivals prescient rivals partitions of refinement, but then we assume they're sort of informationally the same size, well, they somehow have to match each other, and then the net result is you show that there's this function exists. And in fact, it's the original function here that mapped from rival states to causal states is really F inverse. So the same thing. We can disagree over vocabulary, but that's it.
Proof of isomorphism.
Yes, right. Prescient rivals the same size are isomorphic. That's the point. Yep.
Do you know it's vertical?
There's some kind of messy border cases here. Yeah, and then you. Yeah. So. Right. So if you roll up your sleeve and do the measure theory, it gets kind of grungy, actually. Yeah. That's why I'm calling all these things proof sketches, at least to get some idea. We can talk about the properties, give this kind of high-level view of like why it's interesting, and then when we really got interested, it's and then so we'll get into some of these subtleties later on, but once we have the basic ideas down, so it's this is just the quickest of roadmaps. Okay. I think this is like the final property, and namely that if we look at the causal state process and any prescient rival, equally predictive, that the sort of induced stochasticity is smallest with the epsilon machine. In some sense, the causal states attribute the least random process, internal process. So the way we're going to say that is that this, now remember, this is order 1 Markov chain, so we've captured everything over the causal states. You can show that this state-by-state uncertainty, it's like an entropy rate in this case, that this is always less than any other predictive rival. Okay, now this one, it's an example of where whiteboards would be much better. It doesn't really, it's a longish proof, so I'll try to get through this, but we'll hop back and forth a little bit. Okay, so what we're going to do, and this brings in a lot of these information identities. Okay, so epsilon machines have minimal state stochasticity. Well, so we're going to start out here making some observations that we have to do some groundwork before we actually get down to just talking about the rival state process and the causal state process. And we're going to be moving from internal processes, the state process, to observations and back again. Okay, so the first thing we're going to do is focus on the uncertainty in next symbol and next state, given the previous state, for the epsilon machine. Okay, it's just an information identity. This is, when I'm thinking about this, this is just some joint distribution, right? The uncertainty in x and y given c, and I just apply this information identity. I have a choice, but I put y out first here, uncertainty of y given z plus the uncertainty in x given y and z. Okay, so I just rewrite this in terms of this joint, conditional joint uncertainty into the uncertainty in the next symbol in the future, given the previous state, and the uncertainty in the next state, given the next symbol and previous state. Okay. But by unifilarity, that second term is 0. Right. If I know what, okay, I'm starting in a state and I know what symbol I'm going to see, by unifilarity I know uniquely what state I'm going to go to. Well, I'm saying the uncertainty. There could be no next state, but I would know that. So this is it. There. Okay. So yeah. So we just showed that. This is that. Okay. And then we can do the same thing for this, predictive rival, what we're looking at. Same kind of next symbol, next state, given previous state. And I pull out the uncertainty in the next symbol and the uncertainty in the next state, given the symbol and the previous thing. I know that this is 0. It's a non-negative number, so I'll just throw it away. So I get this inequality here. That this is going to be less than that, or that this in particular. However, I know that since this is a prescient rival, and I can go from the prescient state to a causal state, that this uncertainty for the next symbol is the same as using the causal state to predict that. But then I just showed that this, on the previous slide, this single step symbol uncertainty is also equal to the joint uncertainty of next state of this. But again, these are redundant, as you feel like. Okay. So now we can also expand this joint conditional uncertainty in a different way, in a complementary way, where I don't bring out the first symbol here, but I pull out the next state given the previous state uncertainty, and then I have the uncertainty of the next symbol given previous state and next state, two edges. This is the symbol on the edge. Okay, but now I can put these two things together here to show that since these are equal, I just showed this is lower bounded by this quantity, that this right-hand side is greater than or equal to this. So what I'm trying to do here is pull out terms that look like this, because I just want to make bounds on the rival internal state process and the causal state internal process. Okay, so I don't find that overly informative. It's one of those proofs where you have to see the final result and then go back and read it again. Okay, so, right, so I can expand and the right-hand side of this guy, again, like we did before, and then rearrange so that now what I'm writing out on the left-hand side are the two terms we were interested in. This is the entropy rate, essentially, of the rival state internal process, entropy rate of the causal state Markov chain. Now we have this difference here, and then that's lower bounded by this difference. Given the past and current causal state, the uncertainty in what symbol I'm going to see. So you should think about state, state, and then this variable is labeling the edge between them, the transition between them. And the same thing here. I've got these two rival states, and there's a symbol between them. However, we know that we can go from rival states to causal states through this function g. Then that induces a way of going from pairs to saying that pairs of causal states are actually a function, g prime, just the extension of g to pairs over pairs of rival states. So, right, that means, again, it's like the data processing inequality. I'm trying to compare these two terms here. So the uncertainty in the next symbol, given this compound knowledge of the previous state and current state, that's actually a function of, I should say, the causal state, previous state and next state. Which causal states there are, that's a function of this. And therefore, it increases the uncertainty in the next symbol. Right? I'm just using this identity here. Right? Uncertainty x given y is less than uncertainty in x given some function of y. Right? All the g can do here is throw in useful information away from y that will make x look more uncertain. That's all I've done here. Right? Because the causal state pair is a function of this detailed information I had. But then that means, given this inequality, this is positive. Right? This uncertainty, I just showed that this uncertainty, single step, is larger than this uncertainty, therefore it's positive. Therefore, this difference is positive, and therefore any rival, the internal state process of any rival is larger than the randomness or internal state entropy rate of the causal states. Like I said, this would be better written out on 3 boards, and I can go back and forth and point at things. So it doesn't. So the Epsilon machine does not ascribe, willy-nilly extra randomness to a process. You could do that. I mean, it's a hidden process after all. So you could have things that are at the observation level equally predictive, but had a more complicated internal mechanism. So this, in some sense, is showing that the mechanism is least stochastic compared to alternatives. Okay, well that's pretty good. I mean that's sort of all the hard work here. Maybe just some other connections, and then we'll finish up. So there is an interesting discussion in Elements of Information Theory, Cover and Thomas, about relationship between information theory and statistics. And they kind of recast a lot of the ideas in mathematical statistics and in information theory terms. One of them is this historical notion of a sufficient statistic. So we have this, just a little background of what this means. We have some random variable x, and we assume it's distributed according to some given distribution that maybe has some parameters denoted theta. So x is Gaussian distributed, and theta would be mean and standard deviation. You have some parameters. So imagine the distribution for x has some parameters. So then we have this function, here I denoted t, maybe that should call f. There's some function of this. Think of, oh, I'm going to calculate the running average of the samples of the Gaussian process to get the mean, right? So the idea is you have a statistic, which is a function of samples, that helps you estimate the parameters of the distribution. Right? There's another function which, through samples, would give you the standard deviation. Okay. So the idea of a sufficient statistic is that this function of x contains all of the information you need to estimate theta. Or said this way, I mean, when we compare things, what do we use? We use mutual information. So what this says is the information theoretic recasting of this concept of sufficient statistic is that the mutual information between the random variable and the parameter you're interested in is the same as the mutual information between this function you're calculating of x and the random variable. Yeah?
So is it also true that t of x would, or x to t of x to theta would be a Markov?
Exactly. Yes. Right. Right. So that's another way of casting what a sufficient statistic is. Exactly right. Yeah. Mm-hmm. Right. And then the notion of a minimal sufficient statistic, not so much talking about size, like we were just talking about, but the idea is that this sufficient statistic is minimal if it is a function of every other statistic you could calculate. So punchline here is that the epsilon machine is a minimal sufficient statistic for a process. Okay, so in other words, we can calculate anything we want. So the sketch here is that, well, first of all, the maximal prescience gives sufficiency. Namely, the mutual information between estimating the word distribution and the causal states is the same thing as estimating the word distribution in the past. It's essentially just rewriting that prescience out in a different form for mutual information. But it turns out every prescient rival is a sufficient statistic. Anything that does optimal prediction is essentially a sufficient statistic. But then we just established that in the space of all the alternative optimal predictors, the epsilon machine is the smallest. And just because the rival states are refinements. So basically, it's a minimum sufficient statistic. And the punchline of the lesson is very simple. You can calculate every statistic, every property you want from a process's epsilon machine. A lot of this is just actually recasting things we already talked about with the other properties, but at least it makes a connection to this other discipline of statistics. So just to summarize, we showed that the epsilon machine is the optimal predictor. It has the lowest prediction error of any rival, unconstrained. But of the optimal predictors, it's the one of smallest size. And then if you come up and you say, oh, I've got an optimal predictor with smallest size, it's essentially equivalent to the epsilon machine. So it's a unique model of the process. And we produced all of its statistics. And the causal states give you the causal shielding. Gives you the sort of operational sense of what the causal states do. They're very much, it's like the generalized notion of Markovianness of summarizing the past. So now to sort of look ahead a little bit, I want to start using these things to do things. It's been 2 weeks now of setting up the framework, trying to argue how we have answers to these questions that certainly the information theory discussion Winter Quarter brought up. Like how do we do modeling? Can the data tell us? And the claim is now more or less established with these proofs that there is a process can tell you how it should be represented. And there's a way of optimally doing that. And there are these ancillary properties like, well, actually, if you want to even calculate how random it is, the entropy rate, you have to use these causal states somehow, the Epsilon-Machine. So now looking forward to using the Epsilon-Machine to start talking about dynamical systems more generally, how they store and process information. So the next lectures kind of sort of a theme here, namely thinking about sort of the natural, physical, biological, chemical, could be social world if you like, neurobiological world, in terms of how it stores and processes information. And we're going to use the Epsilon-Machine to do this. So there's this notion of intrinsic computation, not running Microsoft Excel on a waterfall. I don't mean that. I mean the waterfall on its own terms, or the neurobiological system on its own terms, or the spin system on its own terms. How much past does it remember? How much of the past does the process store? Where in the system's state space is that information stored? What's the architectural structure of how that information is stored? And then how does that stored information get used to produce future behavior? So, in short, how much of the past does a process store? Well, I already said it. The claim, and we'll have to show this in applications, is that the statistical complexity is the amount of history, an information theoretic measure amount of history of process stores and its state information. What's the architecture of the information stored? Well, we have to look actually a little more at the structure of the Epsilon-Machine. But the answer to this question is the Epsilon-Machine. That is the architecture. Well, I might want to pull that back if I was looking at the Epsilon-Machine. It's coming from a symbolic dynamics description through generating partitions, pull it back to the dynamical system. So there's a little bit of work there, but the short answer is the architecture, number of states, the actual set of transitions, that is how the information is stored. And then how is that stored information used to produce future behavior? Well, we have kind of a proxy for that, the entropy rate, how much information is generated by a process. But there are other aspects to these we'll get to. There are other ways of thinking about things that we already talked about, the bound information, the ephemeral information, decomposition of the entropy rate, and we'll be able to pull all of that out of the Epsilon-Machine. And so that the computation mechanics and Python package in the Sage browser has all that stuff built in. So I'll be able to calculate these quantities and talk about how to estimate those things. And get a much more detailed picture of how processes store information, process it, generate it. And in particular, using this structural picture we have, namely the causal states in their transition organization, refine our notions of different kinds of information processing. So that will be it until Tuesday, unless you have questions.